Picture this, a factory in the sky. Imagine a factory, not on the ground, but floating high above the Earth. This is a space station. It orbits our planet every 90 minutes, but this station does more than just host astronauts for science experiments. This station builds things. It is a factory in the sky. The idea is simple. We can make products in space that are difficult or impossible to make on Earth. This orbital manufacturing could change specific high-tech industries forever. It will not replace all our factories on the ground. But for some very special items, space is a better place to build. This concept is not science fiction. It is based on real physics and economics. The environment in orbit offers unique advantages. We call this environment microgravity. It is a state of continuous freefall. Things are not truly weightless, but they behave as if they are. This changes the rules of manufacturing. We can also use the near-perfect vacuum of space, and we can harness the constant, unfiltered sunlight for power. These are the fundamental reasons to even consider building a factory hundreds of kilometers above our heads. Microgravity is the first and most important advantage of orbit. On Earth, gravity is a constant force. It pulls everything down. This causes sedimentation, heavier particles settle. It also causes buoyancy. Lighter fluids and gases rise. In freefall orbit, those effects almost disappear. Imagine trying to mix two liquids with very different densities on Earth. You stir, but they quickly separate. In microgravity, they can be mixed perfectly and stay mixed. That enables new metal alloys with incredibly uniform properties, which is extremely difficult to achieve on the ground. Another effect of gravity is stress on growing materials. Think about a delicate crystal for a high-powered laser. On Earth, the crystal's weight creates internal stresses and tiny defects. Those defects reduce performance. In microgravity, the crystal grows suspended, not supporting its own weight. That lets larger, more perfect crystals form with far fewer defects. The same principle applies to Zeblan optical fibers. Gravity-induced imperfections on Earth limit their clarity. Beyond microgravity, space provides a near-perfect vacuum for free. On Earth, building large industrial vacuum chambers is expensive and complex. You must constantly pump air out to avoid contamination. In orbit, the vacuum is just outside the door. That pristine environment is ideal for thin film coating and ultra-pure material processing. You can make electronics and semiconductors cleaner and more efficiently than in terrestrial factories. Finally, the sun. In low Earth orbit, a station gets direct unfiltered sunlight for 60 minutes every 90-minute orbit. That's a powerful, reliable energy source. Large solar arrays capture it to run factory systems. There is a period of darkness when passing through Earth's shadow, but overall the supply is abundant and predictable. That steady power is crucial for energy-intensive processes like melting metals and growing crystals, which need stable, uninterrupted energy for long runs. It's a free utility that helps offset the high cost of operating in space. Now let's discuss the cost equation, the tyranny of the rocket. The single biggest obstacle to manufacturing in space is cost, specifically, the cost of getting there. Every kilogram of material, every spare part, every robotic arm must be loaded onto a rocket and blasted into orbit. As of today, in 2026, the cost to launch 1 kilogram to low Earth orbit is still measured in the thousands of dollars. While this price has come down significantly thanks to reusable rockets, it still dominates the economics of orbital manufacturing. This is what we call the tyranny of the rocket equation. It dictates that anything we make in space must be incredibly valuable. This creates a clear economic threshold. For a product to be viable, its final market value must cover the round-trip launch cost and factory overhead. Visual launch cost versus product value, per kg, steel, water far below break-even, Zeblan fiber, semiconductor wafers near above, that immediately rules out bulk goods like steel beams or concrete. Launching raw iron ore or cement ingredients costs far more than the finished product is worth. The math simply does not work. So the focus is on small, lightweight, high-value items, a few grams of a life-saving drug, a spool of ultra-pure fiber optic cable that weighs only a few kilograms. Let's look at an example. A company wants to produce unique semiconductor crystals in orbit. A batch of raw materials might weigh 10 kilograms. At $2,000 per kilogram, that's $20,000 just to reach orbit. Then add operational costs for the factory. The final crystals must sell for well over $20,000 to be viable. If Earth-made crystals sell for $15,000, there's no business case. If space-made crystals can fetch $100,000, profitability becomes possible. High launch costs also force design changes. Engineers must prioritize extreme efficiency and miniaturization. Every gram counts. Factory components need to be lightweight yet durable. Processes must produce very little waste because wasted mass is wasted launch dollars. So, who are the players willing to foot the enormous bill for orbital manufacturing? A flow diagram showing private ventures, space agencies, or defense with arrows pointing to an orbital factory, arrows labeled profit, strategic capability, and national security. The participants can be grouped into a few key categories, each with its own set of incentives. First, private, venture-backed companies. Incentive, profit. They bet on products produced in space, ZBLN fiber. Specialized protein crystals for drug development. Produced in space with superior quality commanding a premium price on Earth. Pioneers taking on high financial risk hoping to capture a brand new high-margin market. Second, government space agencies like NASA or ESA. Incentive, enabling future space exploration. Imagine a large deep space telescope. Imagine a Mars-bound spacecraft. Instead of building the entire structure on Earth, it's easier to launch raw materials or modular components and assemble or manufacture the final structure in orbit. In-space manufacturing is a strategic capability reducing risk and cost for future large-scale missions. They fund research to build the tools they'll need for tomorrow. Third, the defense and intelligence sector. Incentive, national security and strategic advantage. Needs cutting-edge sensors. Needs advanced communication devices. Needs high-performance optics for satellites. Microgravity-made crystal for a surveillance laser, 10% more efficient, or an antenna that's lighter and more powerful. Those performance gains give a significant tactical edge. Value here is measured in superior intelligence or defense capability, not dollars. They are often early adopters of expensive, high-performance tech. Finally, research institutions and universities. Incentive, the pursuit of fundamental knowledge. Microgravity lets them study the physics of fluids. Study combustion. Study materials, science, in ways impossible on Earth. They pay for access to orbital facilities to run experiments. Their work may not produce a commercial product tomorrow, but it builds the scientific foundation for future commercial applications. The data they gather helps everyone understand processes, better reducing risk for commercial players who follow. The success of space manufacturing is not a gradual slope. It is defined by a series of sharp tipping points or thresholds. The most critical threshold is the launch cost per kilogram. If launch costs remain at $2,000 per kilogram, only a handful of products are viable. If they fall below about $500 per kilogram, a whole new range of manufacturing processes becomes feasible. This single number acts as a gatekeeper for the industry. Companies watch rocket launch prices with intense focus. Another key threshold is operational reliability. Orbital factories must operate autonomously in a harsh environment. Business plans might require 5 years of operation to be profitable. If a critical system fails after 6 months, the investment is lost. A reliability threshold must be met. Investors will likely wait until prototypes run continuously for a year or more before funding full production facilities. That creates a multi-year delay to profitability. These factors create powerful feedback loops. 2 feedback loops, positive loop and negative loop. A positive feedback loop could accelerate growth. For example, if one company succeeds and proves a product is profitable, it de-risks the concept for investors. More factories, higher launch demand, lower launch costs, more products viable. One success could trigger a cascade of investment and growth. Optimistic scenario entrepreneurs hope for. Robotic system fails catastrophically. Product batch contaminated. Insurance premiums for all space ventures would skyrocket. Higher insurance costs are passed to customers, raising product prices. Prices fall below profitability, causing demand to collapse. A single failure could chill the industry, scare away investors and set progress back by years. The system is fragile, and it's uncertain which loop will dominate. While orbit offers advantages, it also imposes severe constraints that add complexity and cost. Energy is a prime example. While sunlight is plentiful, a station in low Earth orbit passes into Earth's shadow for about 30 minutes every 90 minutes. For processes that require continuous stable power, this is a major problem. The factory must therefore be equipped with large, heavy batteries to store energy from the solar panels and provide uninterrupted power during these eclipse periods. These batteries add mass, and mass adds to the launch cost. Designing an efficient power storage and distribution system is a non-trivial engineering challenge. Another major constraint is thermal control. In the vacuum of space, you cannot get rid of waste heat easily. On Earth, a factory uses fans to blow air over hot equipment, or uses liquids to carry heat away. This process, called convection, does not work in a vacuum. Heat can only be shed through thermal radiation. This means orbital factories must have large radiator panels. These panels, often seen as wings on space stations, radiate heat away into cold space as infrared light. The size of the radiators needed is directly proportional to the amount of waste heat the factory generates, adding yet more mass and complexity to the station's design. Maintenance is perhaps the most daunting constraint. On Earth, if a machine breaks, you call a technician to fix it. In a factory 400 kilometers up, that is not an option. Sending astronauts to perform repairs is incredibly expensive and risky. Therefore, orbital factories must be designed for extreme reliability and remote maintenance. This means using robotics. Robotic arms must be able to swap out failed components, clear jams, and perform routine servicing. This requires a level of automation and remote operation, sometimes called telerobotics, that is far more advanced than in a typical terrestrial factory. The reliability of these robotic systems is paramount. Finally, all these systems must survive the harsh radiation environment of space. Outside the protection of Earth's thick atmosphere, electronic components are bombarded by high-energy particles from the sun and deep space. A single one of these particles can damage a computer chip, causing a glitch or a complete system failure. This requires the use of radiation-hardened electronics, which are much more expensive and often less powerful than their commercial, off-the-shelf counterparts. Every computer, sensor, and controller on the station must be designed to withstand this constant assault, adding another layer of cost and design complexity to the entire enterprise. If these challenges are overcome, and orbital manufacturing matures, it will not replace Earth's industrial base, but it will augment it in critical ways. We would see the rise of a new two-planet supply chain for certain products. Raw or semi-finished materials would be launched from Earth, processed in an orbital factory, and the high-value finished goods would then be returned to Earth for sale. This would create a new economic sector focused on orbital logistics, quality control for space-bound payloads, and the design of space-certified components. Earthside factories would adapt, shifting to become suppliers for this new off-world industry. This new steady state would have tangible benefits on Earth. The availability of superior materials could spur innovation in terrestrial industries. For instance, ultra-efficient medical imaging devices made with space-grown crystals could improve healthcare diagnostics. Vastly improved fiber optics could make global communication faster and more energy efficient. It would also create new jobs, not in space, but on the ground. We would need more rocket engineers, robotics specialists, mission controllers, and experts in space law and orbital logistics. This is not about moving jobs to space. It is about creating new categories of jobs on Earth to support a space-based industry. The regulatory and geopolitical landscape would also have to evolve. Nations would need to establish clear rules for orbital manufacturing. Who is liable if a defunct factory creates dangerous space debris? How are export controls applied to sensitive technologies built in the international environment of space? These are complex legal and political questions that will require new international treaties and agreements. The first companies to succeed will not only be technical pioneers, but also pioneers in navigating this new regulatory frontier, setting precedents for decades to come. We have seen the physics that makes it possible, the economics that makes it hard, and the thresholds that will determine its success. We understand the incentives for those who would pay, and the daunting technical constraints they must overcome. The system is a complex interplay of cost, risk, and immense potential reward. It is a logical, step-by-step progression, not a sudden leap. But even with all this analysis, as we stand here in 2026 looking toward the future of industry, one fundamental, unresolved question remains. What specific product will be the first to truly break through, to consistently and profitably be made in space and sold on Earth? Today is March 2, 2026. We are standing at a fascinating point in this story. The first small steps have already been taken. Experiments on the International Space Station have proven that certain processes work better in microgravity. Private companies are now designing dedicated, uncrewed space stations to scale up this production. The question is no longer if we can manufacture in space. The question is when it will become a profitable, sustainable business. We will explore what actually happens when you try to build a factory in orbit. What scenario should we explore next? Share your ideas below. You've been watching Ifverse, where imagination meets possibility. See you in our next reality.